Hi. So first of all, I want to just say that I'm just so excited that I have this opportunity. I mean, it's my first time in Australia, and I'm here talking to you about Ruby, so that's just fantastic. So thanks for inviting me. It's a great honor to be here. And since probably many of you don't know me, short introduction. So my name is Piotr Solnica. I'm a software developer from Poland. I live in Krakow. And I work a lot in open source, mostly Ruby libraries. You can find my profile on GitHub, obviously. I'm Solnik there. You can also follow me on Twitter and check out my blog, solnik.eu. I don't write often there, but sometimes I write about things that I've learned or some interesting libraries that I'm working on, so feel free to check it out. And I work for IceLab, where we are building web applications using dry-rb and rom-rb. And today I will be talking about rom-rb. So persistent space off, and you look at rom-rb. So why a new look? Coincidentally, just 2 or 3 weeks ago, we released ROM 3.0, which was a huge release that also included the first stable version of ROM SQL adapter, as well as first stable version of ROM repository. So today we're going to just take a look how it works and see how it works. So the plan for today is to focus on 4 big topics. The first one is why rom-rb was created, like explain the motivation behind the project. Then I would like to talk about how it works. We're going to take a look at its main components without going too much into details. Then I would like to talk about how it's different from other RubyGems, because rom-rb is quite a unique gem. And I want to talk about its philosophy. And the last part is a short one about future challenges and how you can help. So let's get started. Why rom-rb was created? So this is a difficult question. And the simple answer is to solve a problem, obviously. It's not a toy project, it's a real project that aims to solve a specific problem. And that problem is separating persistence from domain layer. As a community, we've been looking into this problem since roughly 2009 or 2010. I remember like first discussions that were happening around 2010, and the reason why we started discussing this problem was mostly caused by a growing number of applications that started to suffer because of growing complexity. And what people identified as one of the reasons for this problem, this problem with complexity, was just active record. Not necessarily a library, but a pattern that we use. So we started looking into other ways of working with databases in Ruby. And one of the things that came up was separating persistence from domain layer, so using a different approach. So to understand why this is a problem and why it's good to solve it, we need to take a look at active record. And again, not the library, just the pattern. So active record is a pattern that makes a huge assumption. It basically says that your database schema is your domain model. But the truth is that it's just not true. You cannot say that my database schema is my domain model because it's just a false statement. You cannot say this. So what active record is doing is basically saying that you're going to treat your database schema as if it was your domain model. And all the differences, we're just going to ignore them. And if they start biting you, well, you'll have to deal with that on your own. So we have a lot of libraries in Ruby that implement active record pattern. Obviously, the most popular one is active record from Rails. So it's an ORM, first of all, so it's very object-oriented. And it looks pretty nice. We think about objects. So we create a project, we find a project, we change its title, we save it. So it looks like there's no database, right? Now the trick is that there is a database, and we actually want to use it, right? So what we end up doing is find by SQL and then just some custom query. Now this may look innocent, but what really happens in a bunch of projects is that people start to use a lot of custom queries. And so this is from Discourse. It's a Rails-based discussion forum. And they have quite a lot of custom queries that are pretty advanced. So I'm not sure if you can read this, but as you can see, it's complex, right? It's a lot of code. So what people end up doing is that they start adding their own ad hoc solutions so that they can simplify some parts of their systems. Like Discourse has its own SQL builder that allows them to define custom queries and get results mapped to simple structs. Now, you may think that this is something that is not that surprising because Discourse is a big project, so things like that happen in big projects. It's not really about the size of the project, it's more about the complexity of the domain. I worked on projects that were pretty small, like 8,000 lines of code, 10,000 lines of code. It's not that much code. So they were like small to medium, but the domain was pretty complicated. And this is what always happens, that eventually you need to start to use your database effectively. Now, I want you to focus not on how it's done, like how we use our database, but why we want to use our database effectively. So regardless of the tool that we're using, it's just important to understand why we want to have our own application data, because that's what it boils down to. It's about application data that are specific to our application, right? And I know that in an object-oriented language like Ruby, people just really like to talk about objects, sending messages, like object design. And we like treat data as something that's ugly, right? That we want to hide it. It's a pretty common thing in object-oriented design. But the truth is that application data is like the most important part of our systems because all the systems are processing data, right? They take some data from some place and then turn it into some response, or the other way around, they receive some input, turn it into something and store it in a database. And that's why application data is extremely important. And because it's such an important concept, it should be easy to define our own application data. And it's an interesting thing to realize that even in applications that use ORMs like Active Record, you still have your own application data. It is just harder to see it. Like you need to read the code, understand what it's doing. It starts with some objects like Active Record objects, but eventually it ends up with a different structure, like some JSON or some data that is used in a HTML template, right? So we can like see the application-specific data by just understanding what the code is doing. And it's not what you have in your database. It's specific to your application. Now, since we want to have our own application data, it should be easy to retrieve it from the database. If you start writing your own SQL builders and like working around your ORM, it pretty much means that your ORM is no longer helping you, right? And the same story about making changes to your data. It's pretty common that the input that your application receives is just not compatible with the data structure, with the database structure, right? So we need to transform it in a way that you can persist it. And the reason why it's needed is pretty simple. What we store in our database is different from what we have in our application, right? The way we define our tables, our columns, the way we specify associations between our tables, this is optimized for our database. It's optimized so that the database can work efficiently, but not necessarily optimized for our application. Now, last but not least, data integrity is really crucial for healthy applications. Fixing broken data on production is not just risky, but it's also stressful and time-consuming, right? And it's the database that is the best tool that you have to ensure data integrity, right? We cannot say that we're gonna just have great Ruby validation DSL and we're done. It's important to put emphasis on the fact that the database has this mechanism and we should use it, right? Now, Active Record, the pattern, doesn't really provide or encourage any of the things that I just mentioned. And it's not that Active Record is wrong, it's just that by definition, this pattern is just not meant to solve these problems. It's a pattern that is meant to simplify persistence layer, right? So it removes a bunch of abstractions and just narrows it down to a simple idea that our database schema is directly mapped to our objects, and we're going to use these objects to make changes in our database, to query our database, and that's it. And if there are differences, then you're on your own. So rom-rb was specifically created to address these issues, to provide a real alternative to common Ruby ORMs. But how does it work? So first of all, ROM is not a typical monolithic library. It's more a toolkit. It's a collection of core abstractions with high-level abstractions built on top of the core ones. And I'm going to just show you like the top-level abstractions today. So we have 3 main abstractions: repositories that are used to fetch application-specific data. They use relations that talk to the database, and relations are provided by adapters, which means that every adapter can support all kinds of database-specific features so that it can be optimized for a given database. And then we have changesets that are used to make changes to our data. So let's start with repositories. So repositories encapsulate accessing application data. So let's say we're building a blog in 15 minutes, of course, and it has posts. Shocking, I know. So in ROM, you don't have models that are connected to the database. You define repositories. So you define repositories typically for some individual concepts within your application. So we have an idea of a post. So we create a post repository that is connected to posts relation. Now, let's say we want to have a feature that we fetch posts by their slugs. So we define a method called get. And it accepts a slug, a string, and then we use post relation to actually create the query and retrieve a single result from that query. Now, what's important here is that your application uses repositories to get its own data rather than performing various queries directly. So it's not using relations directly. It's using your own interface that you define in your repositories. So this way, we would just reduce coupling between your application and persistence. Now, it's really just a convention in ROM. Repositories are provided by an external gem. It's not an integral part of ROM. It's an external component that you can use, and we encourage you to use it. And through this simple convention, we simply hide various details like database-specific DSLs from your application so that your application uses your own repository interface. Now, this is much simpler than some crazy complex ORMs that provide all kinds of very heavy abstractions, like abstract query interfaces, for example. We just don't have that. And we just give you a tool and say that, OK, here's a repository abstraction. Just define your own persistence abstraction with it. Now, repositories use relations, and relations encapsulate database queries. It's a definition that is OK if we're talking about SQL, although relations can talk to all kinds of databases, not only SQL. In fact, they can talk to YAML files or CSV files, doesn't matter. But in SQL, we can say that they encapsulate queries. So a relation can be defined explicitly as a class, as your own class. And it's configured for a specific database backend. So here we have a relation that is configured for SQL. Relations have schemas. And schemas define attributes with types and all kinds of information that is specific to a given database. In SQL, this pretty much corresponds to database tables, table columns, right? We can infer these attributes. So here we have infer true, so we don't have to type them manually. And then we can define associations. This is pretty common thing. It works in a similar way as an active record. So we say that post relation belongs to users, and it has many tags. Now notice that this class is called posts, right? It's not a singular name, it's posts. And the reason why we have this convention is because relations represent data. They don't represent a single thing, they represent collections. Now, what you typically do with relations is that you define your own methods. So here we have an index method. It's an instance method. So unlike models in active record with scopes that are class methods, here we have instance methods. These methods are chainable, just like scopes, but they are also composable, which means that you can compose them into nested data structures. So here we have index method. So let's take a closer look. We call these methods relation views, which is kind of similar to actual database views. So it's a smaller subset of the data that we have in our database. So let's say we're building a feature that is an overview with posts. So it's a table with ID, title, author, and tags. So what we're doing here is that we select ID title, and we select first name and last name and concatenate it. And we give it an alias called author. We want to have author column, but we don't have authors. We have users with first name and last name. So what you would typically do with an ORM is that you would just load all the posts with all their attributes and along with authors. And if you're not careful, you're going to end up with n+1. But what we're doing here is that we fetch exactly what we need because we can. Then we just join users and group by required columns. So we end up with a query like that. And then we can use it in our repository. So let's say we have this overview feature. So we're going to implement a method called overview because it's a meaningful name. And we then use aggregate with tags, which means that we're going to fetch posts along with their tags. And then we're going to narrow down the result to our index view so that it's simpler. Then we can easily use it, and we're going to get back structs with posts and their tags. Now, this has some pretty nice benefits. So let's say we want to add sorting. So a typical feature, you click on a header and it changes the sorting, right? So what we can easily do is to add sort keyword and then just use order method, right? And then we can sort by author, even though there's no such column, but it exists in our own relation view, right? So it's just pretty straightforward because we do exactly what we need to do because it looks the way it actually looks on the user interface, right? But let's do something more complex, like add a filtering feature. So we can filter by, for instance, title or authors. So we're going to add a new parameter called filter. Then we're going to reduce this filter by passing our relation view. And then we're going to apply all additional restrictions based on filter. So the important part here is this. We're not passing symbols and values. We're actually asking relation for a specific attribute, which has some bonus nice behavior that it's going to raise an error if there's no such attribute. And the trick here is that we don't have author, right? It doesn't exist in our database, but we have an attribute like that. So when you take a look at author attribute, you're going to see that it's actually a column, a virtual attribute that you can use to create restrictions for where clause. So if we do this manually, we're going to see that it returns a Boolean expression with equality operator. And it's going to be dumped into valid SQL thanks to SQL that is used under the hood. And so it just works. We don't have to do anything manually. So we end up with an interface like that. So we can filter by author, and it just works. But let's say we want to add some more detailed filtering, like by individual relations and their attributes. Like let's say we want to filter by tags, right? Not just attributes from our table, but also by some external attributes. So we need to extend our overview method. We're going to accept a hash that can filter hash that can be deeply nested with names of relations and their attributes. So if it's not a hash, we're going to maintain our original behavior. But if it's a hash, we're going to just do the same thing, so just reduce it in the same way. We also need to join additional relation and just apply the restriction. And then we can call it by passing filter with specific relations. In this case, it's tags and their names. We can sort by author, and that's it. It just works. So the cool part here is that this is pretty flexible. Like you can add new columns, you can add additional data to the resulting view that comes from other relations, and this will just stay the same. It will just continue to work. And the only place that you will have to change is either your relation view just your relation view. So that's not the end of the story because after all, we're using an object-oriented language, so working with plain structs, it's sometimes not enough. So sometimes you just want to have your own objects, right? So let's say we want to use some view decorator. So ROM allows you to ask for your own objects. And it's pretty simple. So let's say we define our own class, and let's say it's going to return a list of tags separated by a comma. And then we just ask repository for our own objects, just like that. And we get back not the built-in structs, but our own objects. So that was about reading. As you can see, it's quite different. It works differently. But what about changing data? So in ROM, we have Changesets, which is like a separate part of ROM that is just dedicated to do just this, to simplify creating and updating data in your database. So a simple example of a changeset is that you ask a repository for a changeset with some new data, and you can commit it because changesets are standalone objects. If you commit a changeset, it's going to just give you back whatever the database returned. Now, you can also save changesets through repositories, and in this case, it's going to turn the response, the database result into a struct. But there are actually two big reasons why you want to use changesets, and the first one is associating data. This is actually a pretty complex problem to solve, and libraries like ActiveRecord are absolutely amazing at handling association, so we need that as well. And in ROM, changesets are used for that. So here we create a transaction, and we create a new user and a new post, and we're going to associate our post with the user, and then we just close the transaction. It's going to return a post with user ID foreign key automatically assigned. So this is pretty handy. It's also a new addition. A few months ago, we wouldn't be able to do that. But there's also another big reason why changesets are so useful, and it's the idea of data transformations, which is like the first-class concept in ROM. So let's say we want to create new users, but our system receives hashes like that, so just author key. We don't have first name and last name, we just have authors. So what we need to do is to obviously split this value into first name and last name. So changesets allow you to define your own classes, your own changesets. And inside these classes, you can define transformations. We have a method called map, and you can pass in an argument, so let's call it a user, which will be our input hash. And then we can do just whatever we want. So let's say we're going to just do what we need, so split author value into first name and last name. But we can also apply additional transformations using a slightly different syntax. If you don't pass any argument, you will be able to use a built-in DSL for transformations, which is provided by a gem called transprog. So it's a trivial example, so we're going to just reject keys and pass in an array with author, because we don't need author key. So this is a DSL that is actually pretty powerful. As I said, it's a trivial example, but this DSL comes with many built-in transformations, and you can transform data in all kinds of ways, so it's pretty useful. Once we have our own changeset, we can ask repository for its instance, give it some data, and when we dump it into a hash, we're going to get back what we expect to see, so first name and last name. We can save our own changesets through repositories, just like with any other changeset. In this case, it's going to return a struct with first name and last name. Another interesting thing about changesets is that they work with both hashes or arrays with hashes, or in fact, an array with any object that can be cursed into a hash. And in this case, the changeset will just create multiple users and give them as a result. And this is actually pretty cool because under the hood we can do some tweaks, like for instance, in Postgres we use multi-insert automatically because we have dedicated database commands per each database type. So this is pretty nice. So that was a really quick overview of main ROM components. There are tons of features, but I would like to talk a little bit about how ROM is different. As I said, it's a pretty unique Ruby library, and the first surprising fact is that it's a library written in Ruby that is functional. Now, the whole core gem is pretty functional. It takes a lot from functional programming. And probably the best example showing the functional nature of ROM is that relations that are used to fetch data from the database, and they are objects, but they also have function semantics. So they are actually functions that you can call. Now you can call a relation, and in this case it's going to hit your database, get the data, and return a materialized relation. We call them relation loaded. Now this is this hasn't been done for fun, as a joke or whatever, or to make something cool. It was actually built like that so that we can compose relations. Since they work as functions, it means that we can compose them as functions, right? So this is what happens under the hood when you're asking for aggregates, so for nested data structures. It boils down to composing relations into nested data structures. So if you ask for posts with their tags, what will happen is that we're going to fetch posts and then pass them to tags, and then tags will find all the tags for particular posts. And that's it. So that's a pretty nice example of implementing a feature that is pretty complex, because eager loading of associations is a pretty complex feature. But with this simple idea of composing relations, it turned out to be pretty simple, if not trivial. So at the same time, ROM is object-oriented, right? It's written in Ruby. It uses a lot of objects. So here's a proof. I talked about repositories. So repositories are objects. Unlike active record models with class methods, repositories are objects. So repositories use relations, and relations are objects. Relations have schemas, and schemas are objects. Schemas have attributes, attributes are objects. Changesets are objects. Changesets use commands, and commands are objects. And all these objects are just composed together to create some more advanced abstractions. Now, at the end of the day, blending functional programming with object orientation turned out to be a really big win for this project. It was such a big win that eventually we adopted a bunch of functional techniques and some principles in other projects. And that's how rom-rb was born. And this design and some of the principles that we have when building gems makes it really easy to achieve composable gems. Now, with composable gems, you can create a library that focuses on the essence. It doesn't have to do all kinds of stuff because it can reuse other abstractions from other libraries. And when it's easy to compose gems, it's much easier to just build them. And here's an actual outcome of that when it comes to the amount of code that we have in ROM. So ROM core library has 3,322 lines of code. Our SQL adapter has 2,102 lines of code. And my favorite example, repository with a ton of really advanced features like automatic mapping, like automatic commands, like changesets, is just 1,080 lines of code. Now, even when we add all of that, it's just 6,504 lines of code. That's very little code if you take into consideration all the things that you can do with ROM and all the features that we have. Now, I really think that gems that are built with composition in mind, that are just really easy to reuse and easy to become a foundation for some other abstractions, are a great win for the ecosystem. And we already have a couple of really big proofs, like Tim already mentioned in his keynote, Hanami and Trailblazer. These are great examples of gem composition, library composition. But it's not that simple to achieve that, actually. It's not like that one day you're going to say that, okay, from now on I'm going to build composable gems, and then magically you start doing that. You actually need to follow certain, maybe not rules, but guidelines. The first one is no monkey patching, right? You cannot say that you released a gem with monkey patches and say that it's reusable, because it's not, right? The second thing is that it requires reduction of global state. There are lots of gems in Ruby that heavily rely on global state. And in Ruby, everything is mutable, right? So they basically rely on global mutable state. And it also requires good separation of concerns, which is a pretty hard thing to achieve, because you really need to have a good understanding of what you're doing in order to come up with the right abstractions. So it takes time, right? It takes effort to experiment and see what your library really needs to do. And it also requires more objects and less classes and modules. Libraries that are very easy to reuse are libraries that provide objects rather than classes or modules. And it really boils down to the known truth that composition is better than inheritance. With inheritance, we have classes with their global state. We have modules that can be mixed in, so we have multiple inheritance like that. And it's much harder to manage than simple objects that can be composed, objects that are much more predictable than classes and modules. Now we have some real-world examples how gem composition is beneficial for the ecosystem. So, of course, ROM. ROM uses SQL, the library, as the backend for ROM SQL adapter. It uses dry types as its foundation for relation schemas, and dry types is a gem that provides a really tricky abstraction, and it made building schemas with their attributes much simpler. We have dry initializer that is used across multiple ROM gems for simplifying definitions of rather more advanced constructors with things like default values and validating types so that we cannot instantiate an object that is invalid, and actually much more. Now, why SQL was so easy to use as the foundation for ROM? Well, first of all, it has no globals. When you use SQL and connect to a database, you get back a connection object. Then you can ask this object for data sets that correspond to database tables. Data sets are mainly immutable, and in fact, in SQL 5.0, they will be immutable, like literally frozen, by default. And we already enabled this in ROM SQL, so in ROM SQL, all data sets are already frozen. And also, SQL provides a lot of beautiful small abstractions, things like SQL functions or SQL expressions as a base for implementing custom classes for all kinds of SQL expressions. It's just absolutely beautiful and very easy to reuse. And similar story with ROM. Why was it so easy to use as the foundation for Hanami? Again, no globals. We don't use any global objects at runtime. We use objects exclusively. But also, every part of ROM is first class. Like, every public API is treated as a first class feature, and we have a lot of abstractions, so it's very easy to build other things on top of it. And of course, we don't rely on mutability. All objects in ROM are not meant to be mutated. We don't have public APIs that would mutate them. And it makes it much easier to use this library as a foundation for your library because it's more predictable because of that. So that was about differences between ROM and typical Ruby gems and about philosophy. And what about future challenges? ROM is a very big project overall. It's a toolkit that consists of many gems, and we always have new challenges, right? So the biggest one is finishing other adapters. We have a bunch of adapters on production already, not just SQL, but also ROM HTTP, ROM Dynamo, ROM CouchDB. But there are plenty of adapters that are just in prototype phase, right? And we just need to finish them. Also performance. ROM is already pretty fast, but we can make it faster, of course. So for instance, it uses transproc gem for in-memory transformations, data transformations, and if we can make transproc faster, ROM will become faster. We can optimize fetching single objects in ROM. We can add support for prepared statements, and just hundreds of micro-optimizations. And of course, docs, right. As I mentioned, we have all public APIs treated as a first-class citizen in ROM, so we want to have everything documented. And it's just a never-ending story, and we're always looking for people to help us with docs. But the simplest thing that you can do is to just use it. Even if you don't have an actual need for it, just try it out and tell us what you think. With more feedback from people, we will manage to make ROM much better, faster, right? And that's all I have for today. So thank you.